Hello, transportation engineering class. Today we will be talking about stopping side distance and crest vertical curve design. Before starting the discussion today, I want to very quickly recap what we learned about the stopping side distance. If you remember, it does have two components. The first component is the distance that is being traveled while the driver is making decision on pushing the brake pedal. We have also another component, which is the distance that is being traveled while the brake pedal is shifted and the car is reducing speed. We want the summation of these two distances to be less than the distance that the vehicle has from an object. If that's the case, the vehicle is going to stop without hitting the object. If that is not the case and the summation of these two distances is more than the distance of a vehicle and an object, we are going to have a collision. Now, I want you to think about a crest vertical curve. As you can see in this slide, I have a crest vertical curve. The length of the curve is L. You can see the PVC, PVI, and PVT. And now I want to put a car and an object on this curve. So you can see the car on the left-hand side. We have an object on the right-hand side, and the distance between the two on horizontal plane is S. So we want this distance to be more than the distance that is required for the driver to make the decision, and also to reduce the speed of the car from whatever the initial speed is to 0. You also can see that I have an H1 and H2 on this graph. H1 is going to be the height of the eye of the driver, and H2 is the height of the object. So these are two important factors that influence the stopping side distance and eventually influence the design lengths of the curve. So by using the characteristics of parabola, and remember, whenever we talk about our curves, we are talking about equal tangent curves, we can show that the minimum length of the curve, or LM, that we need to maintain for safe stopping side distance can be found by these two equations that I have here. The first equation, or equation 313, is for the conditions that length is more than the stopping side distance. Equation 1314 is for the conditions that length is less than the stopping side distance. So what is the first equation? The first equation says that the minimum length should be equal to A. Remember, A is the absolute value of G2 minus G1. So L is equal to A multiplied by stopping side distance square over 200 in square root of H1 plus square root of H2 raised to the power of 2. The other equation is quite different. In that one, the minimum length is 2 times of the stopping side distance minus 200 into square root of H1 plus square root of H2 square over A. Now, we can simplify these two equations by using design values for H1 and H2, and these design values are coming from AASHTO. So what do you think is a good number for the height of the driver's eye, and how about a good number for the height of the object that we want to avoid? So the design value for driver's eye height is 3.5 feet. And for the object, we know that if the object is too short, we probably don't care about it, as the vehicle can go over the object. But the objects that are at least 2 feet are those that we are concerned about, and we want to make sure that the driver has an opportunity to see them and avoid them by stopping the car. So the design value for H2 is 2 feet or 600 millimeters. Now, what is going to happen if we plug in these two numbers in the previous equations that I showed you? We can plug these numbers in those and actually simplify them a bit. So if you do so, the first equation, which was for the conditions that the length is more than the stopping side distance, becomes Lm equal to A in stopping side distance square over 2158. And the other equation would be 2 into stopping side distance minus 2158 over A. We can see that these equations now look much simpler and a lot more usable, at least to me. Now, we have these equations in the metric form. I have put them in this slide for your records. Of course, in the course, in this course, we are using only US customary, and we will not be using metric customary or any equation in metric units. Now, we have a table here that gives us the stopping side distance and rate of vertical curvature, or K, for different design speeds. And essentially you can use K, as you can see in future slides, to determine the length of the curve. Now, again, we can see that the speed goes from 15 miles per hour to 80 in increments of 5. So for each of these, you can see the stopping side distance goes from 80 to 910. And for each of these, the K is calculated. And also you see a design value, which is essentially rounded up to the nearest integer value. So for example, if you have 43.1, you can see that the design value is rounded up to 44. On the left hand side of this table, you see all values in US customary. On the right hand side, you see metric units. So again, we are interested in the left hand side of the table. And please keep in mind that this K is the same K that we visited previously in this course, and the equation for the K is L over A. Now, a few things that I would like to highlight in this table. The first thing is that all the calculations are done for G of 0, or assuming that the slope is 0. So that may seem a little bit odd, because we know that we are on a crest vertical curve. We are either going uphill, downhill. We may actually be on a level train or with 0 slope, but most of the times we are not. Why do we do that? Now, the main reason is that if you are driving down the hill, you are gonna need more stopping distance. We know that the gravity is not gonna help us. But at the same time, if you imagine you're driving down the hill, you know that you can see more. So yes, your car is gonna stop more, but at the same time, you have more eyesight and you can see the objects a little bit better. So we are assuming that these two somehow help each other or cancel the effect of each other out. On the other hand side, when you are driving up the hill, so you don't see much, but at the same time, if you want to stop your car, you can stop it a little bit faster. So what we are thinking is that, yes, I don't see enough, but if I push on the brake, it's going to stop faster. So in a way, you can see that both on downgrades and upgrades, unless they are not, unless they are really excessive, we can assume that the grade is 0 because in one of them, you see more. Yes, you can stop your vehicle a little bit harder, but you see a lot more, so you can react earlier. On the other hand side, on upgrades, you don't see enough, but as soon as you hit the brake, the car is gonna come to and stop. So for that reason, a lot of times when you have these curves and you want to find stopping sight distance, you just assume that the grade is 0, unless we have a specific grade that's and that is specifically asked from you in a question or in an example that, okay, do the calculation for this specific grade and find the stopping sight distance. If that's not the case, we assume that the grade is 0 or the slope is 0. So I think this is a very good point to go through an example. And again, like all previous examples, I'm gonna go through the question, then you're gonna stop or pause the videos for 5 minutes. You're gonna do it on your own, and then we're gonna go through the solution. So we have a highway that is designed up to AASHTO's guidelines. The design speed is 70 miles per hour. And at one station, we have an equal tangent vertical curve that connects grades of +1 to -2. So this is a crest vertical curve. First you go up the hill, then you go down the hill. So we want to determine the minimum length of curve according to AASHTO standards to meet stopping sight distance requirement. So please pause the video at this point for 5 minutes and go through the example and then continue. So what we will be doing here is that, again, we're going to assume that the grade is 0 or the slope is 0. So the design speed was 70 miles per hour. If you go to table 3.1, you will see that the required stopping distance is 730 feet. So that's the distance that you need as a driver to react and also to stop the car. Now, if you remember the equations that we saw, they have two parts. One says L is more than stopping sight distance. The other part says L is less than stopping sight distance. So we have the stopping sight distance, but we don't know the lengths. We want to find out what is the minimum design length, and then we are gonna either go with that or a little bit longer than that, but we don't know if that's going to be less or more than stopping sight distance. So as an engineer, you need to assume, to make an assumption here. Let's assume that L is more than stopping sight distance. Find the value of L, and then we check if it is more or less than the stopping sight distance. If it's more, we are good. If it's less, we need to do something. So let's start. I'm going to assume that L is more than the stopping sight distance. So I'm going to be using the equation that is given for that condition, which is Lm equal to A in stopping side distance square over 2158. So my G2 is -2, G1 is 1, so A would be equal to -2 minus G1, which is +1, which is equal to 3. And that would be 3%. So that's what I have here. We also found stopping side distance to be equal to 730 from table 3.1. So you can see that I'm multiplying 3 by 730 square and divided by 2158. That gives me a value of 740.82 feet. So that's the minimum length that I need on that curve. You can see that this length, 740, is more than 730 feet. So that means that the assumption that I made at the beginning is satisfied. So I'm good. So the length of the vertical curve should be at least equal to 740.82 feet. Now, I want to talk about how we should be using those two equations, because should I assume L is more than stopping side distance? Should I assume it's less than stopping side distance? So what you want to be doing is always to assume that first, assume that L is more than stopping side distance. Go and find the value of L and see if that assumption is correct. Now, the main reason that we do that is really two things. The first thing is that in majority of the cases, L is going to be more than the stopping side distance. Second is that the equation that we have for L greater than stopping side distance is easier than the other one. So it's always more convenient to assume L is greater than SSD or stopping side distance, find L and just check to see if that's the case. Also, this equation gives us a linear relationship between A and minimum length. We know that L, length of a curve, is equal to K into A. So if you just put these in the equation that we had, we just find out that K is equal to SSD square over 2158. So just to summarize, we always assume that L is greater than stopping side distance. We use the equation that corresponds to this condition. We solve the problem. We check if the L that we have found is greater than stopping side distance or not. If it is, we are done. We are good. If it's not, we need to go and use the other equation. So we have another example that I want to go through. This is example 3.6 from the book. We have a highway that is being designed to AASHTO guidelines. So the design speed is 70 miles per hour. We have an equal tangent vertical curve. We must design this curve to connect a +1 to a -2 slope. This problem is identical to the previous problem in terms of input. What we want to do is to determine minimum length of the curve according to AASHTO standards to meet stopping side distance requirements. Now here, rather than using the equation, we want to use the K values. So I would like you guys to pause the video for 3 minutes or so and try to work this problem out, and then afterwards we will go through the solution. So the first thing that we need to do here is to find the value of A. If you remember, A is equal to the absolute value of G1 minus G2, or G2 minus G1, really doesn't matter. So that would be 1 minus -2, that would be 3%. The next thing that we want to do is to find K from table 3.2. To do so, you need to go and find the K that corresponds to a design speed of 70 miles per hour. Going to the table, you will find out that that K value is 247. And if you remember, K was equal to L over A. That means that L is equal to K multiplied by A. So that's what we do here to find the minimum lengths. L is going to be equal to K into A, or 247 into 3, or 741 feet. You will see that it's just slightly different than what we found from the other equation, but we know that this is more than 730 feet of stopping side distance, so it is okay, and we can use this value for minimum lengths of the curve. This concludes our discussion about Crest vertical curves, and in the next class we start talking about sag vertical curves. Thank you.